Welcome to the electrostatics lesson on electric potential energy and electric potential. We're going to start with electric potential energy, which is the work done to bring a charge either toward or away from another charge. We're going to begin our discussion around the values of electric potential energy and whether they are maximum, minimum, zero, etc. And to do that, we're going to investigate the electric potential energy near a large unit positive charge. To test the electric potential energy of this positive charge, we of course would use a test charge, a charge that is positive and small. Where would we take and start with our test charge? Well, as we previously learned, we would start with it near the positive, because we know that that positive is going to repel it. At release, at the moment we release this charge, we know that it's going to have zero initial velocity, therefore it's going to have zero kinetic energy, and by law of conservation of energy in general, not mechanical energy, but still law of conservation of energy, that means that the electric potential energy is going to be its max value. The symbol for electric potential energy is capital U subscript E. So this electron starts out at zero and obviously is repelled away, in which case it will start off slowly and then speed up until it reaches infinity, at which point this test charge would be going its maximum possible velocity. If that's true, that means it would have maximum kinetic energy, and when it reaches infinity, its electric potential energy would be zero. Everybody has a pretty easy time understanding this scenario. The thing to take away from this is that electric potential energy is always zero at infinity. Now, I've put two spots on here, spot A and B, and if you were asked which spot has greater electric potential energy, how would you answer that question? Well, the first thing you would do is you look at what your source charge is, which is positive, and then you would take your test charge and put it at the closest of those 2 points. In this case, it'd be point A. And you say to yourself, okay, I'm going to let go of it at the closer spot, picking closer because you'd want to be closer to the positive. And when I let go of it, what happens? Well, it is going to move towards B. That means its velocity is going to increase towards B. That means its kinetic is going to increase towards B. That means its electric potential energy is going to decrease as it goes towards B. So your answer would be that A has greater electric potential energy. Now let's look at the scenario for the electric potential energies and energy relationships for a negative source charge. Well, where would we start with our test charge? We would start with it as far away as possible. Where as far away as possible? Well, far away as possible is at infinity. But if we're truly at infinity relative to this source charge, then if we let go of it, nothing's going to happen because we're at infinity. And we're reminded that the electric potential energy at infinity is zero. However, if we take this test charge and move it just inside infinity, give it a little nudge or do a little bit of work to get it started, that initial velocity is zero, therefore its kinetic is zero, therefore its electric potential energy would be a max value. This charge is going to accelerate, increasing in velocity towards the negative, and just at the moment before impact, that test charge would be going its maximum velocity. That means it would have its maximum possible kinetic energy, and therefore the electric potential energy would be at its min value. Now, this is a point of confusion, because how can a charge, the test charge, go from having 0 electric potential energy to its max value in basically a very, very, very small distance? And this is complicated and confusing at times, but all we have to remember is that electric potential energy is always 0 at infinity, and then just think through, what would this test charge do if I let it go at this particular spot? Any increase in velocity means an increase in kinetic, which means a decrease in electric potential. Okay, now let's talk about the equation for electric potential energy. And we're going to start with electric potential energy. Its symbol, by definition, is work done on a charge. And remember that work done is force times change in displacement, or F times delta R. Well, the force is going to be, for two charges, K Q1 Q2 over R squared times delta R, which we'll just say is R, the distance that we move it. And what do you note? Here, this R would cancel out the square, and we would get K Q1 Q2 over R. Hence the equation for electric potential energy. And if you were asked for work, you understand that that's the same thing. And that should make sense to you based on the concept of the work-energy theorem. All right, let's next take a look at electric potential. Electric potential is the work done per unit charge to move a charge from one location to another. And as we look at this equation, the symbol for electric potential is V, capital V, which is equal to the work done per unit charge, which is equal to the electric potential energy per unit charge. The equation for electric potential energy we just derived is K Q1 Q2 over R. Question becomes, what is the Q in the denominator? Well, just like we learned in an earlier lesson, the charge in the denominator is the charge that you put at that location. It's not the source charge, it's the charge that you move to some location you want to know the electric potential at. We have a double fraction, which we simplify by multiplying both the numerator and the denominator by the reciprocal of the denominator. And when we do that, we get KQ1 over R. This would be how you calculate the electric potential for one charge brought from one location and placed at some distance R from a source charge, Q1 being the source charge. What this also means to you is you don't need to know the value of the charge brought to that spot. All you need to know is how far away from the source charge you are, and you can calculate the electric potential at that location. The units for electric potential are volts, named after Voltaire, and the symbol is capital V, making electric potential one of those rare quantities that has a quantity symbol and a unit symbol that is identical. There are three other terms that you may hear substituted for electric potential, and they are voltage, potential difference, and difference of potential. We're going to get technical at first with regards to difference of potential or potential difference, and you'll see that modeled for you in problems to come.